All right, welcome to another one of our videos. In this one, we are going to be exploring how we can build an evaluator for reverse Polish notation expressions. And let's get right into it. So first, what are we talking about, right? So when we are when we're looking at math expressions, the thing that most of us are accustomed to have this form 1, 2, 3, where we see the operators in between the operands, the numbers, right? And this notation is called the infix notation. There is also other forms of notations, right? We have the postfix notation, and we have the prefix notation. And the postfix notation simply means that the operator comes after the operands. So if I wanted to represent what I have for the infix notation as postfix, then that would be this, right? So you see here, we add the 1 and 2 first, and then we take that, and then we add 3 to that result, and that is the postfix notation. The prefix notation is the reverse, right? So we would do something like this, where we have the operator in front. So here we're adding 3, and what are we adding 3 to? We're adding 3 to the addition of 1 and 2. So that is the prefix notation. Now, reverse Polish notation, RPN, reverse Polish notation, is synonymous with this postfix way of representing things. So this is the reverse Polish notation. And that is what we will be building an evaluator for, which you can see some of the code for on the opposite side of the screen here. So this is what we want to highlight, right? And you can already see that there is a benefit to the prefix and the postfix notation, in the sense that we don't have to worry about the order of operations necessarily, because that's enforced by the structure of the expression, right? So in this, we see that we add 1 and 2 first, and then we add 3 to that result, as opposed to here, this could be evaluated in a few ways. We could have 2 plus 3 and then add 1, or 1 plus 2 and then add 3. And the way we try to enforce order of operations, infix notation, is how we introduce parentheses around sub-expressions, right? So we won't have to deal with that with the postfix notation. So what is this RPN evaluator going to do, and how does it work? Well, we can see some usage examples here. And if you're not familiar with Unix command line, this echo bit here simply just means print, right? So I'm providing this reverse Polish postfix expression to the RPN evaluator that we have written here, and these are one and the same, these are equivalent, and it will evaluate it and give us the answer. So let's do a few examples. So we already saw where we have 1 and 2. So 1, 2, and 3, right? This gets reduced to, well, we have 1 plus 2, and that becomes 3 plus 3, and then that becomes 6. Okay, let's do what we have in our usage example over here. We have 1, 10, 30 plus and multiplication. What happens? Well, we have 1. The 10 and the 30 get added. So that's 40. And we are left with 1 times 40. That's 40. So we've already gone through 2 operators. Let's go through 2 more. So let's say that we have 1, 2, 3, 1, 2 minus 2 and plus here. Well, we see that 1 and 2 would get subtracted, but pay attention to this because this is 1 minus 2, right? So this is negative 1, right? And then 2, and then plus, and then this becomes 1. Okay. So, and then we can have division as well, where this is just 1 divided by 2, which is 0.5. So one thing to note here is that are the commutative properties of these operations, right? Can you move the numbers without that changing the result of the expression or the meaning of the expression? And for addition and multiplication, changing the numbers don't matter, right? 1 plus 2 is the same as 2 plus 1. 1 times 2 is the same as 2 times 1. However, the same cannot be said for subtraction and division. And so that's something that we're going to have to be cognizant of while we're writing our code to solve this problem. So the input to this program, this RPN evaluator, is going to be a reverse Polish notation expression, a postfix expression like this, right? And notice the significance, pardon me, the significance of the spaces between these the operands and the operators, right? It carries a meaning, as opposed to in infix, the space doesn't quite matter, right? Like this is the same. But for postfix and prefix notation, the space does matter because that's how you delineate the numbers, right? If I had 3, 2 here, that becomes 32 and not 3. Although I am now seeing that it may not matter as much for the operands itself. The operator when it follows a number, but to keep things clean, we'll just keep a space between all our symbols. And so we will, I'm going to take the walkthrough of this in a top-down manner, because I feel like it's easier to conceptualize that way as opposed to going from bottom up, right? So what I'm doing here is I'm taking some input, whether that's the user typing and entering that, or it's passed via a pipe. here, this standard in, then we're going to tokenize that input, the expression. And what do I mean by tokenize? Well, let's look at the tokenize function that I created here. So we're going to take this expression that's a string, and we are going to break it into a list of strings, right? And to do that, I'm merely splitting the expression by the spaces to get the individual components. So for example, just take this. This would then become 1, 2, plus 3, plus. That's what happens when I tokenize the expression. Okay. I wrote 2 versions of this, recursive version and then iterative version. I'm going to walk through the iterative version first. And so this iterative version takes this these tokens, the list of strings consistent of the numbers and their operators, and it's supposed to give us a number as output. Now, the key data structure in solving this problem is a stack, right? So, and you can see that a bit here, where let's say we add 1 to the stack, we add 2 to the stack, we encounter an operator, we take 1 and 2 off the stack, we apply the operator, so we get 3, and then we add that result, because it's intermediary, back onto the stack, and we continue. And so that's how this evaluator works. So we initialize an empty stack, and for each token, right, 1, 2, plus 3, plus, we're going to consume that token. Don't think about what that means just yet. We're going to consume the token, even though I just can't explain what that means. But we're going to consume that token given the current stack that we have. And once we've gone through all the tokens in our list of tokens, then by the end of it all, the last thing on the stack should be our result, right? So, and you can see that from here too, where we had 1 and 2 on the stack, then we reduce that to a 3, so now the stack only has 3, but then we add 3 again to the stack, and then we encounter the plus, and then we take those 2 3s, add them, get the 6, and so the 6 is the last thing that's on the stack, and so we just take that off as our answer. And so we can now dive into what's going on with consume, but I also want to just show that the transformation of this iterative solution to a recursive solution is not a difficult one to make, right? So we are preserving the same interface where we take a list of tokens and we want to return a number. But within that, we declare, we define an iterative, a function that's meant to be recursive, right? And this is written in accumulator style, where the thing that we are iterating over is this list of tokens. Iterating over or recursing over is the list of tokens. And we are using the stack in the same way that we were in the iterative solution. We're adding things to it, popping things off as we encounter operators, applying the operator and putting things back on to the stack before we move on to the next call of this function. So what happens? Well, if we run out of tokens, then we get the result from the stack, right? Same thing we did up here. Once we've finished going through tokens, we get the result. If we do have tokens, then we work on the current token, right? We consume the current token. It's exactly what's happening here, right? For the current token, we consume it, whatever that means for now. And we go on ahead and process the rest of the tokens with the new updated stack that we have. And we do that all the way until we hit our base case of having no tokens at all. And so what I like about this this organization here is that it makes it, at least to me, and I hope to you, it makes it easy to see how you can transform a rather basic for loop into a recursive function. So I hope that I hope that was that's somewhat enlightening or illustrative or informative to you. So let's look at what's happening with let's look at what's happening with consume token, right? So it's a function that's called with a token and a stack of values on there, right? So here we go. It consumes a token given the current stack and returns the updated stack. So what do we do? Well, we have a certain set of operators that are supported by this evaluator, right? If we were to write an expression that that has modulo in it, or some other mathematical operator, then this would not work, right? Because it's just not part of the vocabulary of what we need to evaluate in the postfix notation that expressions that we're creating. So I defined and initialized a dictionary here that maps the token to a function to its corresponding function. And Python has this convenient module called the operator module that has function equivalents for a lot of the built-in operators. So we have our addition, we have subtraction, we have multiplication, and we have division represented as true div. So what do we do? So we have this token, and so we want to know, well, if the token is in the supported operators, then we want to take the last two items off the stack, because these operators are binary operators, right? They need two things in order to work, right? And so we take two things off the stack. And well, if we happen to encounter an operator and we can't take two things off the stack, And that's a problem. It means that we've written our expression incorrectly, because the constraint here is that we need two things, right? Now, if we have the two things, then we can apply the operator. And so this is, here I'm just using the token to key into the supported operators to get the function. So if this were the plus token, then we'd get the add function. If this were the minus token, we'd get the subtract sub function. And if this were the asterisk token, we get, and so on, right? And we apply that to the numbers that we took off the stack. And then we, after we've calculated our result, we append that result to the stack, right? And so that's our new stack. Now, something to note here, and I think this is perhaps one area that some folks might encounter a little bit of trickiness, because we pop so we have 1 and 2 here. We pop 2 off the stack, and that's encoded here as num1. And then we pop 1 off the stack, and that's encoded as num2. And perhaps I shouldn't use the name num1 and 2, because that implies a bit of order in there, where you might want to use num1 before you have num1 be the first number here. My bad. But what we want to know, what we want to be cognizant of, is that the order of these matters for the subtract and the division. They don't matter for the plus and the multiplication. So might as well just have them in a way that indicates that it matters, right? And so the second thing, the second number that we pop off, should be the first number that we apply. So in that case, this is, we would pop 2 off. In this case, we would pop 2 off. This is num1, 1. This is num2. And for this division, we want to do 1/2, which is num2 over num1. And the same thing goes for the subtraction, right? And so that's why I'm passing in num2, the second item that was popped, as the first argument to the operator. I hope that wasn't too confusing. If it was, drop a comment. If you think that was spot on and I spent enough time on it, also drop that in the comment. Feel free to explain it in your own words to folks in the comments who might not understand it as well. Now, if we encounter just a number, then we are just going to append that number to the stack, right? And I just have a utility function here for converting a token to a number in a way that respects its type, whether or not it's a floating point number or if it's an integer number. Don't really need to peer into this too much. You can if you want, but we're just converting a numerical token into an actual number data type. Now, if this fails, let's say we had the modulo operator in our expression and we don't support it, then we would try to convert that to a number. That would fail, and we would get a syntax error here. Fine. And the other core function to this is the get result from stack. And there's just some defensive stuff in here. This could have naively been written as just popping the last item of the stack and returning that as the value. but in my consideration that the expression might be malformed, it may be the case that we run out of tokens and somehow we end up with more than one items, more than one numbers on the stack at the end of our processing. And so that would mean that we have some extra tokens that have not been that we have not processed, right? And what would be an example of that? Let's say we had 1, 2, and there we go. That might be it. So here we would reduce this to 3, and then we would add 3 onto the stack. At that point, we would be out of tokens, and we would find that we have 2 things on the stack instead of 1. And that's just like, well, we have leftover tokens, right? So that's a problem. It's an example of extra tokens. And that is it. Those are the 2 core functions for getting this to work, right? How we consume a token by adding things to the stack and popping things off the stack and applying the operators in the correct order, and getting the result from the stack. There's also, I also just wanted to show just a little bit how the recursive function would evaluate things. And that's for this example of where we're given 1, 2, 3, and I left off the quotes just for easy typing here. 1, 2, 3, multiply and plus, and it's just showing what the tokens are for each recursive call and what the stack is for each recursive call. And we can see the tokens list shrinking bit by bit until it's empty, and we can see the stack getting built up until it encounters an operator. So in this case, it's going to encounter the times operator. It's going to reduce 2 and 3 to 6. Then it's going to encounter the plus operator and reduce 6 and 1 to 7. And at that point, we just pop off the 7 and return it. So that's how we build reverse Polish notation evaluator. Thank you for watching. Subscribe, leave a comment. Let's have a discussion about this in the comment section if you feel so inclined. Feel free to also check out the code on GitHub or on medium.com. I'll add some links in the description to that as well. All right. And that is a wrap.